Welcome students, in this class we are going to talk about conservation law. Now what is conservation law and why is it so important? Essentially we will be talking about something which is, so mathematically speaking, it's a first order equation. Okay, so equation will look like this: ut plus f of u x equals to 0 and u at the point x0 is, let's say, phi of x. Okay, here x is in R and t greater than 0, right? So this is the problem which we want to study. Now this is of course a first order equation because the highest degree term is like only 1, right? And see here, if we can assume for now that f is smooth. Okay, so for now assume so f is smooth. It can be c1 c infinity. Okay, so f is smooth. That's all our assumption is smooth. Okay, from R to R. So f is defined from R to R. Clear? So f is a smooth function. Now or I mean it can be from some open interval R, but essentially it is always assumed to be R to R, right? Okay, now have we seen this sort of problem? Of course we did. Yes. So let f of u is u square by 2. Yes. Now you do realize that this is a very valid problem here. F of u can be taken by to be u square by 2 because that's a smooth function. Okay, once you take that, then one becomes ut plus ux equals to 0. U at the point x0 is phi of x. Okay, let's say that's your 2. Now what do you think? Have you seen this problem too? Of course we did. Where did we saw? This is called a Burger's equation. 2 is called the Burger's equation. Okay, and you remember we have solved this too. Yes, and by solving it means that we have found Burger's equation. And so I don't remember the exact video, but we talked about a problem. We talked about a particular phi. So basically we showed that, and we showed in an earlier video. Okay, I don't remember exactly which video was it, but anyways it was the last video where we discussed the quasi-linear case. Okay, first order quasi-linear case. We showed via the method of characteristics, right? Method of characteristics that 2 admits a solution. Okay, no, by solution I mean not global. It is not like a global solution. Okay, because we have seen that, if you remember, for some phi, yes, I don't exactly right now remember what that phi is, but most probably phi x equals to x in that case. Okay, the problem was so this is like don't hold me for to it. I mean, I am like a 99% sure that if you take phi x to be x, you can see that the characteristics of 2, okay, intersect. Yes, as far as I remember. Otherwise you have to work it out. Okay, but probably I did phi x equals to x only that case. Okay, and you can see that the characteristic intersect. What happens when the characteristic intersect? The points where the characteristic intersect, you can no longer define the solution, right? That's what we learned. Okay, characteristic intersects, and the points where they intersect, one can no longer define a solution. Okay, so let us understand again what I am trying to do, so it becomes very clear what we will do it right now. Okay, if you take this example, fu to be u square by 2, one turns out to be our familiar equation, which is a Burger's equation. So this is an example of a quasi-linear PDE, right? First order PDE. Clear? Quasi-linear first order PDE. Now you see 2, the PDE 2, that is a Burger's equation, yes, and with phi of x to be x, a very simple this thing example, phi x to be x. If you take this example, you can see that the characteristics of 2, okay, I don't remember what are the characteristics of 2, but anyway, whatever the characteristics of 2 are, they intersect, okay, and the point where they intersect, you cannot longer define a solution, right? Okay, so basically the solution which you are getting is not a global solution. It's not like defined in whole r cross t positive, right? Okay, so and here one very important thing which we need to remember is, you see, when we say that there it admits a solution, very important thing, there admits a solution. Okay, very important. What do I mean by solution? You need to understand what is a solution. Okay, so solution can be two parts. So in this case, the earlier case which we talked about till now in this course, okay, so by a, let me write it down, I will call it a classical solution of 1. Okay, you guys already know what does it mean. It means that u is in C, classical solution of 2, let's say, u is in C2 of r cross 0 infinity, such that u satisfies true everywhere, right? Everywhere in r cross 0 infinity. That's the natural thing to say. Whenever we say what do we mean by a solution, of course we mean that it's a classical solution. So what does it mean? See, for a u to satisfy this equation, ut, ux, u, all of this has to be continuous, right? For this, all of this to be continuous, it means, so basically you need u, ux, ut to be continuous. Okay, this is continuous means u is in C1. Clear? So that's your classical solution. This is a solution which we will call a classical solution. Okay. Now in this part, conservation law part, we are going to define our solutions a little bit different. So this is a little advanced topic. Okay. So what is our aim in this lecture? Our aim is to define the notion of weak solution. Okay, so the first question is, why do we need the notion of weak solution? Because you do realize, why do we need a new concept? Because this is just the same kind of idea. Because classical solutions are most often than not very easy to derive. You understand what I'm trying to say? Classical solutions are not very easy to derive, which we will just look at it right now. Okay, but by first defining what's a weak solution. So basically, let's define a weak solution. Definition. Okay, I am defining it for this problem. You can define it for, I mean, any ODE or PDE. Yes. Okay, the idea is same. So definition is this. So u, okay, u, that's a function u. So u is said to be a weak solution of 1, to be a weak solution of 1. Okay, weak solution of 1, right? If 0 to infinity, minus infinity to infinity, okay, u vt plus f of u vx dx dt, so this is complicated, plus minus infinity to infinity phi of x v of x0 dx equals to 0. So this particular relation holds. So let's call this relation as 3 holds. for all v which is in CC infinity r cross 0 infinity. Okay, so essentially you take a CC infinity function in the upper half space, and what do you want? You want this particular relation through hold. Okay, so this is an arbitrary relation, it looks like right now, okay, but it is not. We will explain it later. So for now, let's just understand what we just wrote. Okay, so we were given this equation, right? What is our equation? Ut plus f of u times x equals to 0, and there is a boundary condition. Okay, so now what we are doing is we are saying that you have a solution if, see, initially for a solution to exist you need u, ux, ut to exist, right? In our case, what we are saying, for u is a weak solution of 1 is if u satisfies this particular condition for all v which is in CC infinity Rn. Okay, let's look at this condition. See here, u, there is a double integral, whatever it is, don't worry about it. U vt plus f of u vx. One thing to notice here is there is a u here, there is a u here, right? U here, there is a u here, but it does not contain any derivative for now. Yes? Okay. What about here? Here, of course, minus infinity to infinity, you have phi is there, so there is no u. Okay, phi is given to us, so we don't have to worry about it, there is no u. So essentially, you see, we have defined some kind of relation. Okay, I am not coming to how we define it right now. We'll just do it after this. Yes, but for now, see, we defined a relation. We are saying something is a solution. Okay, but we are not using that sort of regularity. So initially, we need u to be at least in C1. Okay. Derivative, you have the derivatives of u, ut, ux, all of those has to exist. Here, if you are using this definition 3, then you see you do not need u to be differentiable. No, if you see you are just taking some integral. So basically, if u is continuous and bounded, that is also good enough. If you can think of it like this, that is also good enough, right? I mean, you do not even need differentiability. Actually, you do not even need continuity. Okay, because you are just taking some derivatives. Okay, for functions. So basically, even discontinuous functions are fine. Okay, as long as they are differentiable, of course. Okay. So essentially, you see what we are doing. See, initially, let's say this is our set where we wanted to find solution. Okay. Now what we are doing is we are going to define. We are defining. Although it does not look like this, we'll just commit to that. We are actually want to define a much bigger set. Okay, so think about it. If you want to find a solution, okay, I give you a small set, I give you a much bigger set which contains the small set. Okay, and if I'm asking you in which set can you find a solution, of course you will go for the bigger one. Okay, that is a safe bet. You see, the bigger one has much more functions, right? So essentially, if you look at the bigger one, there is the chance of getting a solution is much easier. Okay, and also this solution does not have too many restrictions, right? Okay, the other one has a ton of restrictions. Okay, so this is called a weak solution. Clear that u is said to be a weak solution if this happens 0 to infinity minus infinity to infinity u vt plus f of u vx. Okay, so you see all the derivative is going to the test function, this function v. Okay, so v is infinity, you don't have to worry about it. So you just put all the derivatives on it, and there is another term which deals with the boundary. If that happens, then that is called a weak solution. Okay, to be very fair here, now if you ask me that what is this u, why are we not putting this u? Okay, so I will write this u as this. See, so here this is like a small remark. We assume u is in L infinity Rn cross 0 infinity. Okay, sorry, 0 infinity. So what do I mean by this? I mean that this is basically so it means that it is bounded function. Okay, if you know only you do not know measure theory, then just think of this as bounded functions. Bounded functions in Rn cross 0 infinity. It need not be continuous. Of course, it has to be summable. Okay, bounded and summable functions. So let me put it this way: bounded and summable. Huh? Summable. And if you know measure theory, of course you know what L infinity is. Okay, so so essentially we are only looking for, in plain terms, we are only looking for bounded and summable functions such that the relation 3 holds. If that happens, then we say that solution is called a weak solution. Clear? Okay, now let's come to the fact that how did we suddenly derive it and why is so special. So as I told you that we are looking for a in a much bigger set, right? We are looking in a set which is like a L infinity set, not only in C1. So C1 and this is L infinity. Okay, so let us put that thing into context. So we talk about a theorem here. If U is a classical solution of 1, okay, then U is a weak solution of 1. Okay, so what does it mean? It means that if you, let's say that so what is the relation between weak and classical solution? So it says that of course if you can find a weak solution, if you can find a classical solution, okay, I am not specifying how you find it. Of course you can find a classical solution by using method of characteristic in some parts. Okay, so let's just assume that you have found a classical solution. Okay, that will actually instantly imply that that's a weak solution. Okay, now that is what we need to prove. Okay, and that is how you will also understand how this formulation of weak solution is coming. Okay, so let's say that, let's look at the proof of this thing. So of course by classical solution, what do I mean? I mean U is in C1, right? Okay, and what U does is it does ut of xt plus f of u of xt, okay, with respect to x, that is equals to 0 for t greater than equals 0, and u at the point x0 is phi of x. Clear? And it is phi of x. Clear? So let's write it like a 4. This happens for all x in R and t greater than 0. Clear? Okay, for every point you have this, there is a u which does this. Okay, now of course we are taking f to be smooth function, so you can break this also up, which will give you by chain rule f prime. So if you break it up, or equivalently this also means that this is this ut of xt plus f prime. If you f is a R2R function, by chain rule f prime of u of xt, okay, and then you have ux of xt, okay, is equals to 0. So that also you can write it, and u at the point x0 is phi of x. If you want, you can write it like this, okay, but this is just for your information, we don't need it. Okay, okay, now see, once the 4 is true, then assume let f you have a v which is like a c infinity of r cross 0 infinity. Clear? So we are just assuming a function which is a c infinity function, okay, with a compact support. What does it mean? It means that v is equivalent to 0, okay, outside some compact set. And where is this compact set? It is in this r cross 0 infinity, okay, in r cross 0 infinity. Clear? Okay, let we assume it is a smooth function with something like this. Okay, now if it happens, then I will multiply v with this particular term. Okay, so if you multiply it, you see ut plus f of u times x, okay, multiplied by v, integrate it between x running from minus infinity to infinity, t running from 0 to infinity. Clear? this is equals to 0. Okay, so that is there. Now once this is there, I can use integration by parts here, integration by parts, clear? Okay, and of course I can change the this order of the integrals also. Okay, so by using integration by parts and Fubini if you want. Okay, I am not quite sure whether you guys know Fubini or not. Otherwise, whatever you know how you change your integral, we are using that you know, how do I put it, formula. Okay, so once you do that, what happens is, let's look at the first expression. Okay, 0, so minus infinity to infinity, 0 to infinity utv. Okay, that can be written like this, no? Minus infinity to infinity, 0 to infinity u vt d t dx. Okay, I can write it like this, integration by parts. Okay, but there is a boundary term. If you remember, there is a boundary term. Okay, what is the boundary term? Plus the boundary term is minus infinity to infinity. Okay, u v. Okay, t, so 0 to infinity dx. So t, I'm just putting t equals to 0 to infinity dx, right? So u is xt, v of xt from 0 to infinity, and t running between 0 to infinity dx. So that is the first term. Plus let's look at the second term. Here also for the second term, it is 0 to infinity. Okay, minus infinity to infinity. This derivative can be dropped in v. So f of u times vx, okay, dx dt. Okay, if I do that, but there is a boundary term here again, 0 to infinity minus infinity. Oh, okay, so the boundary term here will be f of u times v. Okay, between minus infinity to infinity and dt, that is equals to 0. Clear? This is just integration by parts in one dimension. I'm not doing anything. So one by one. Okay, first of all this expression and then for this expression. Clear? Okay, so once I do that, let's understand what is happening here. Okay, what is happening here? See, f evaluated at u at, so basically if you break this up, this particular term will look like this, no? F of u of x comma t, okay, this kind of thing, times v of x comma t. Now this is evaluated for x is minus infinity to x equals to plus infinity, right? Okay, now you see, the thing is, I don't know what u does at infinity. Okay, that is not our case, but the thing is, I know that v has a compact support outside. You know, it has a compact support. So basically v is 0 outside a compact set. Okay, so basically for x equals to plus infinity minus infinity, if you go to plus infinity minus infinity, what happens is this term goes to 0, right? So v is essentially 0 at plus or minus infinity. Okay, as x goes to infinity, of course it has a compact support. Okay, of course it is 0. So basically this term is gone. I hope this is clear. V has a compact support means v is 0 outside some compact set, right? So of course, as x, if you evaluate x between minus infinity to infinity, okay, x between minus infinity to infinity, v is going to be 0. So this particular term has no contribution in our case. Okay, now here let's look at this boundary term. This boundary term, if you break it up, it will be like this: u restricted to u at the point xt, v at the point xt, okay, evaluated at 0 infinity. So this is t equals to 0 and t equals to infinity. Clear? If you put t equals to infinity in this thing, of course this again v at as t goes to infinity goes to 0, because again v is a compact support function. So after after a bounded set, it is essentially 0. So if you take t towards infinity, that's going to be 0. So you don't have to worry about it anymore. So essentially one part of this is 0. So you are only left out with v evaluated at t equals to 0. This is evaluated t equals to 0. The v might be there, okay, t equals to 0, but at infinity is not there. So basically that particular term is there, so with a negative term, negative sign. Clear? Okay, Okay, so let's just put all of this together and write it down properly. Therefore, what happens is it becomes 0 to infinity, infinity to minus infinity to infinity. Okay, u vt plus f of u vx dx dt plus minus infinity to infinity phi of x. Okay, why phi of x? Because you see minus u, so u at the point x0, t equals to 0 x0, and v at the point x0, right? This term, the boundary term, u at the point x0 is given to be, what is it, phi of x, right? So that is why it is phi of x times v at the point x0 dx equals to 0. Okay, so this is true. So you understand, so this is the case, and this is true, this relation is true for any v. So here and the above is true for any v in c infinity cc infinity of Rn cross 0 infinity. Okay, therefore by our definition, therefore u is a weak solution of 1. Okay, u is a weak solution of 1. So now I hope that this is clear to you how all of this is derived. So essentially, let us again recall, because this is a little advanced topic. Yeah, so we are taking some time here. See, u first of all is a classical solution, means C1 solution, so it has to satisfy the equation at every point. Please remember this thing, very important. The first thing is this: whenever you are talking about a classical solution has to satisfy the equation at every point xt in the domain wherever you are working, right? For every point, very important. Here I am not saying for every point. See, if you have a function v and you are saying it is integrable, does that mean that it has to be differentiable at every point? It does not mean, right? It may not be differentiable at every point, so you don't have to worry about all of that. Okay, so essentially what am I saying is I just need v to be a cc infinity function, u to be a L infinity function. What do I mean by L infinity? I mean that it has to be bounded. So here, if you remember, I am just asking for a bounded function and a summable function, so that you can talk about the integral properly. Okay, once you have that, I don't worry about also continuity. So the solution may be discontinuous also, but and essentially you see since this definition, so what is the difference between the classical and the weak definition? The classical definition is it takes the account the derivatives, right? So you have to talk about derivatives. So hence you need C1. The second definition, Week's definition, does not talk about derivative, but what does it do? It talks about the integrals. The special thing about integrals is you do not always need a continuous function or a C1 function to do that, right? So you only need closed and bounded. Okay, so that is why this is very sorry, not closed and bounded, the summable and bounded. Okay, summable and bounded to define it. So that is the special thing about weak solution. Okay, so this is a much bigger class of function. Why bigger class? Because we have seen that, let's say any classical solution, let's say this is the classical solution, this is weak solution, any classical solution is a weak solution, right? So that is why it is in a much bigger space. Okay, so let us end it here.